Thanks so much for having me. I'll share my screen. Everyone see that? Yeah. Okay, so thanks again so much for the invitation. It's great to be with this group. And what I'd like to do today is actually take you through several approaches I've used for examining heterogeneous treatment effects. And I'll draw on a running empirical application of understanding variation in the impact of college on several wage outcomes to motivate the methods. So the basis of this work is the recognition that an essential feature common to all demographic phenomena is variability across units of analysis. So individuals differ not only in pre-treatment characteristics or pre-treatment heterogeneity, but also in how they respond to a common treatment or treatment effect heterogeneity. And the study of effect heterogeneity can yield important insights into how scarce resources are distributed in an unequal society, which has been a central concern of mine in the study of social stratification, and helps us better understand the roots of differential response to treatments, make sense of differential response. And if policymakers understand patterns of effect heterogeneity, they can more effectively assign different treatments to individuals to balance competing objectives, such as reducing costs and maximizing average outcomes. And so a central aim of this project, which has spanned now a long time, maybe 15 years, has been to demonstrate the usefulness of estimating heterogeneous treatment effects using observational data with empirical applications, particularly those related to issues of social inequality, and develop new statistical methods and tools for estimating heterogeneous treatment effects in demographic research. So this is where I'm headed in today's talk. What I want to do is take you through some of the approaches that I've used leading to the machine learning approach. And each method in some way builds on what we've learned from the prior method, and the outcome builds on what we've learned from a prior outcome as it relates to differential responses. And then I conclude with some thoughts on how to make sense of some heterogeneous effects that we observe given differential selection into treatment. So let's begin with some early work looking at the effects of college on wages using both a propensity score-based partitioning approach and covariate-based partitioning. So first, some substantive motivation. So the effect of college on wages is a classic economic interest with a great deal of work on this topic. Some work on returns to college assumes homogeneity, while other work addresses effect heterogeneity, where the effect of college, or tau here, varies across the population, and there's a distribution of responses. So one long-standing focus in heterogeneous returns to college is how college varies by selection into college. And an influential theory of heterogeneity in economic returns is that individuals who may benefit most from college are also the most likely to attend college. We might call this the positive selection theory. So in a rational behavioral or utility maximization model for the choice of attending higher education, questions about access to college and the effects of college are intrinsically intertwined. People make decisions about whether or not to pursue higher education on the basis of that cost-benefit analysis, and then choose college versus non-college if the economic return outweighs the costs. Negative selection is based on research that college-going behavior is governed by lots of factors, cultural, social norms, and circumstances, so that high social background individuals face few risks in pursuing higher education, whereas those with more disadvantaged backgrounds have to overcome considerable odds to attend college, and education is riskier in social and economic ways and may well demand more economic justification. So these theories can be tested by considering variation in economic returns by the likelihood of attending college or completing college, as well as we can also look at some key covariates that are strong factors in selection into college, like family socioeconomic background and measures of cognitive ability and even race. And some scholars have also used instrumental variable methods to try to get at these differences and the effects by selection into college. We've also drawn in our work on an important finding in research on social stratification by Mike Howd, Florencia Torres, and even more recently, some work that's suggestive by Raj Chetty and others suggesting heterogeneity in returns to a college education. So as we see in the figure here, there's little direct relation between origins and destinations for college educated workers. In other words, college acts as an equalizer. And then the relationship is much stronger among less educated workers. So this is just a hypothetical drawing. And if we change the perspective and consider the returns to college, that is, we consider effects rather than these levels, we see that a college degree for those with more disadvantaged social origins can narrow that gap of disadvantage, while a college degree for those with higher social origins could be less consequential. And there's some debate about how strong this equalizing impact of college is. So, this was drawn on a lot of the work by Mike Hout, but some more recent work by Shang Zhao, Dirk Witteveen, Paul Attewell have also questioned how strong the equalizing impact is. But even if we allow some more slope for college educated workers where origins are still related to destinations, we may still generate a pattern of higher returns with those with low socioeconomic origins. So it doesn't actually have to fully equalize destinations for the return to be greater. And it sees particularly poor labor market prospects for workers with low levels of education combined with low levels of other forms of labor market capital, social, cultural capital, which could still generate this pattern. And that's a point I'll return to. So in a recent paper published by Siwei Cheng, Yushia, Shang Zhao, and Mike Hout and I, we also recognize that wage inequality by education is produced gradually over time. And our understanding of whether this economic return is positively or negatively associated with the likelihood of college may depend on an analysis of long-term wage trajectories. So considering long-term wage returns highlights heterogeneity in the life cycle variation of returns. And so if low propensity individuals demand economic justification to go to college and face these considerable social and economic risks, they may be more strongly motivated to generate an immediate economic payoff. By contrast, high propensity individuals can potentially take a longer term perspective and are less driven by that immediate economic return. So that maybe they choose careers with long-term wage growth and accumulate the economic returns to college more slowly. This reasoning is also in line with the literature suggesting differential present versus future orientation of those from more disadvantaged versus advantaged backgrounds. And so what I'm going to do here now is examine the distribution of effects of college completion on wages and draw on data from the National Longitudinal Survey of Youth, a cohort of respondents in the United States who were 14 to 22 in 1979, where I restrict to those who were 14 to 17 in that year to ensure that all the covariates measured occurred before college. The treatment's going to be college completion by age 25. And in this case now, the outcome is going to be wage trajectories. And so we're going to use an iterative procedure outlined by Guido Imbens and Don Rubin to generate propensity scores, which is in some ways kind of like a white box approach, but it iterates through all the possible combinations of variables. Ravaris Moore and Tanvi Shrinky and I, Ravaris was a prior student of mine who's now at NYU, and Tanvi Shrinky is a PhD student in statistics. We have a STATA program to implement this procedure. It's called ITP score. And so what it does is start with a baseline set of theoretically motivated covariates, things we think should just absolutely be in the propensity score model, then considers additional possible covariates in turn, runs through all those possible, iterates through and retains those that increase model fit, and then considers all the possible higher order and interaction terms between those variables that were determined in step 2. And the ultimate model ended up with 1 higher order term, 12 interaction terms, and 22 linear terms. I've also used a random forest model to estimate propensity scores. This iterative approach correlates really highly with the random forest and other machine learning algorithms for estimating the propensity score, but we do, in this case, kind of see what the model looks like, which has some substantive interest for thinking about the processes that lead to selection into college. Here are the covariates I've used in the specification. So there's some socio-demographic characteristics, family background, school characteristics, cognitive and psychosocial factors, early family formation before age 18. So very few, but some were married and some had a child before that age. And there was a fuller list that we went through in the step 2 of the iterative procedure, but these were the factors that were retained, and there's a couple different covariates for some of these. Then I'm also going to eliminate those with no common support, so such that there's no college or non-college goers with no comparable non-college or college goers. So these blue dots are these non-college goers who have no comparable college goers at that level of at a low propensity score, and likewise there's some these yellow data points that were college goers with a particularly high propensity score with no comparable non-college goers. So that redefines our parameter to that which was in the region of common support. Okay, so the question here is, what are the wage trajectories by college completion? And now we're going to look across propensity of college terciles. And the model we use in this paper contains a level 1 random effects model, and level 2 predicts those random effects coefficients using a natural cubic spline of the estimated propensity score, where these 2 knots are chosen at the terciles of the distribution, the propensity distribution. And so here are just some figures displaying the life cycle wages separately for college completion and non-college completion. So the dashed line is no college, the solid line is college, and this is for the propensity score at about 0.1. And this is now across ages 20 through, it actually ended up at age 20. I think we started at 25 through 55. And this is predicted, the y-axis is predicted log hourly wage. And so we see this large college premium among those with the low propensity score, which is largely driven by a relatively somewhat, flatter wage trajectory among those without a college degree. And this suggests among individuals who are least advantaged, a college degree helps them circumvent this kind of bleaker labor market prospect. And for a propensity of 0.3 and 0.6. Among those with the high propensity score, we have also a large college premium, and this is all for men. That's driven mostly by the high and age increasing wage levels, college degree. So those large gains for college graduates from upper income backgrounds are often seem to be driven by those obtaining graduate degrees and the highest earners that really factor into this large premium. But what we have here is a smaller premium for those in the middle of the distribution, and actually large effects for those at the low and at the high level when we look at these wage trajectories over time. And these are the results for women, which suggests that the largest returns are for the lower propensity women. So a stronger pattern of negative selection here, whereas the pattern for men kind of doesn't suggest either. There's large returns both at the low and the high. And so we have more of this. This is a figure now just summarizing the results from the last two slide from the slide for men. So this focuses now on the wage returns, where we highlight that most of the data also fall in these bolded lines, this area, suggesting this kind of U-shaped pattern. So, and this is for age 30, age 40, and age 50. So just kind of a summary. And yeah, there's fewer data points beyond kind of this lower propensity score. And for women, we see more of this kind of L-shaped curve with larger effects for those with a low propensity that start to level off after that. We also conduct some formal sensitivity analyses to explore the direction and magnitude of potential selection bias. So The analysis uses a bias formula that implies a larger bias for low and high propensity individuals than those in the middle of the distribution. And so constitutes a conservative test for the robustness of the finding. And we can see that for men, the U-shaped pattern of heterogeneous returns is quite robust. And then for women, the estimated magnitude and patterns are more sensitive to unobserved confounding, kind of flattens out more. But the moderate L-shaped pattern still roughly holds for various assumptions in the strength of unobserved selection. So we also compare the percent propensity results to mother's education, parental income, and measured ability. So different sources of possible heterogeneity, and we find a particularly large return for those with low parental income. This is for men, and as well as for low measured ability, and some higher returns for high measured ability, especially later in the career. And other work and recent work in economics finds similar patterns. The article by Tim Bartik and Brad Hirschbein find that college has the largest returns for groups from poverty backgrounds and for Black Americans. Other work in economics using instrumental variables, work by David Card and others, have often found large returns for students on the margin of school continuation, returns that exceed average effects, which may reflect some of these more middle level patterns we observe here. Okay, so as I've noted, the generally poor labor market prospects of individuals who come from disadvantaged backgrounds and don't attend college drive some of the large effect for those unlikely to attend. And so seeing those kind of those differential patterns has motivated a look at different types of outcomes. You know, what could be more salient for some individuals than others who potentially, particularly those who have a lower propensity of college. So the basis of a book project I'm working on, that I've been working on for a long time and trying to finish up, focuses on the way in which college circumvents disadvantage for unlikely college graduates. And so what if instead of looking at the impact of a continuous measure of wages, we instead focus on the way in which college enables some college goers, some college graduates to prevent labor market disadvantage. And so again, using the NLSY here, the outcome now is going to shift to the proportion of time in low wage work across the working career. And so in a paper published in Sociological Methodology, not the one on machine learning, but an earlier one, Yushia and Ben Jan and I developed several approaches for studying effect heterogeneity. The first is a parametric approach that we adopted in our early work, and two additional approaches allow for nonlinearity in the trends and effects, where I'm just going to focus on this matching smoothing approach here. And this consists of the following steps. So we, again, just estimate propensity scores for all the units. We match treated units to untreated units with a matching algorithm, and then plot the match differences along a continuous representation of the propensity score, and use a non-parametric model, in this case, a local polynomial smoothing, to smooth the variation in match differences to obtain this pattern of effect heterogeneity as a function of the propensity score. So this is a summary figure of the effects of college on wages by the propensity of college, using now, instead of the approach that I just presented across the career, this is now using a matching smoothing method for the average wage over the career from ages roughly 25 through 50. And here again, you see this kind of roughly U-shaped pattern, especially again where most of the data lie. And this probably less U-shaped than looking at the career trajectories when we were summarizing for the other approach, but roughly in line with that pattern. And then so it may be that we actually have three groups of interest. One of these in the low propensity, one kind of in the middle, and one the high propensity, the way in which we disaggregated before. So I'll get back to that three category stratification. But also now we want to compare to this, compare just the log average wages to this measure of the proportion of time and low wage work. So here we see a pattern that shows the way in which individuals with a low propensity of college have larger negative effects on decreasing labor market disadvantage. Here now the y-axis is reversed to indicate that a negative effect is a positive outcome for the effect of college completion. And we can consider the levels for each of these outcomes. So this is meant to mirror the hypothetical stylized diagram showing the levels for college graduates and non-college graduates to better kind of get a sense for what's driving the results. So for average wages, there remains kind of this slope for college graduates, but there's a large return here for the low propensity, and this levels out. So you have kind of smaller returns right at the high end. For low wages, we see a much stronger kind of equalization for college graduates, and a steeper, this kind of steep difference between the low propensity and high propensity for the non-college graduates. So this kind of directs our attention to the fact that when we consider heterogeneous effects across the distribution of college goers, some outcomes could be more consequential for different subsets of the population. So college may not be a great equalizer with respect to wages, but it may equalize the likelihood of low wage work and other forms of disadvantage that more disadvantaged college graduates circumvent. So I actually explore a large set of similar types of outcomes, indicators of socioeconomic disadvantage in the book project. So focusing now on low wage work, let's return to the 3-category partitioning. And here's just a simple depiction of effect heterogeneity with 3 propensity score strata. The blue effects, now the color coding indicates larger negative effects on the proportion of time and low wage work. And we note the large effects for those with a low propensity. And now let's compare that to other sources of heterogeneity. So lower, 22 percentage point lower level of proportion of time and low wage work versus for the high propensity, a 6 percentage point lower level. And then we can compare this to some key covariates. So here now is the propensity, and then we can add this are parental income category. So the bottom third of the parental income distribution, the middle and the top, and you see a similar type of pattern. These are categories of mothers' education, with mothers with less than a high school degree, those with a high school degree, and those with at least some college. Measured ability categories. So from the Armed Services Vocational Aptitude Battery, this is now the bottom third of the distribution on those scores, in the middle and the top. And then now these are categories of race, where this is Black, Hispanic, and white, and indicating also just the lower propensity of college among Blacks and Hispanics than among whites. So in some ways mirroring disadvantage in terms of selection into college. And patterns are roughly the same across these categories. We could even fill in the whole matrix here and think about intersections across these categories. So thus far, I'm partitioning the sample by either propensity or by selected covariates. And in each of these demonstrations of heterogeneity, relying on a priori generated categories of sources of heterogeneity. Population and social scientists routinely partition samples into the subgroups by characteristics, often gender or race or some other indicator of socioeconomic status, and then explore how the effects of particular events or interventions vary across the population. Those interactions may not represent the most meaningful variation in effects. So often researchers report stratified estimates, often by gender or race, when the differences between the groups are not that significant, maybe substantively not that significant, or even statistically. Long-standing theoretical priors, strong convention that we examine differences by key demographic characteristics often are the things that really drive these decisions. So this is where what takes me where I want to focus the remainder of my time, this approach using recursive partitioning based on machine learning to identify sources of heterogeneity. And this was based on this paper published in Sociological Methodology with two graduate students from UCLA, Bernie Koch and Pablo Geraldo, and a student at Penn State now, Xiaowei Xu. And so the question is, I should say Pablo is on the market and looking for a position in Europe. The question is, are there important sources of variation that researchers may not have considered prior to data analysis? And so, well, we often say that these decisions are based on theoretical priors, and manuscripts are largely written to suggest that these decisions are about which groups to explore occur prior to data analysis. In practice, of course, researchers routinely explore their data, running at times tens or hundreds of regressions to determine if some groups of potential interest show meaningful differences in effect estimates. I mean, sometimes they're just, based on convention and demographic category. Sometimes people are, exploring a lot of different possibilities and then reporting those that do. If they select which interactions to report a result of these kind of background analyses and don't draw on cross-validation procedures or multiple testing hypotheses, penalties, they're subject to incorrectly failing to accept a null hypothesis. Also, the covariates may be most informative when they're considered jointly in some kind of multiplicative way. So sometimes a focus on low-income Hispanic students with high achievement rather than just a broad categorization by race for Black, Hispanic, white may be more informative. But it can be unclear which of the large number of possible joint covariates and thresholds of interest are best to consider prior to analysis. So if we're looking at low income, a category of low income, it may be that the threshold by which we select or determine what's low income isn't clear prior to data analysis. So here we describe this alternative data-driven machine learning approach that uncovers meaningful effect heterogeneity and more transparently depicts the analyses that lead to focus on particular groups. And statisticians and social and computer scientists have made a lot of progress in merging machine learning methods with causal inference. So I draw on this approach by Susan Athey and Guido Imbens and other work by Susan Athey for estimating heterogeneous treatment effects in the potential outcome framework using decision trees. So decision trees are widely used. I'm sure this group is well aware of them, but I'll go over it nevertheless. That use supervised learning algorithm that recursively partitions the data by covariates into increasingly smaller subsets where the data bear greater similarity. So we begin with the full population, a covariate and threshold are selected that best minimize the in-sample loss function, usually the mean squared error within the data, and the algorithm splits the sample into two new partitions. So for example, the root might split on mother's education into two resulting nodes or leaves here if we had the full sample, and then we have a leaf with mothers who didn't complete high school and one with mothers who did. So we partition the covariate space recursively. Within each segment, the resulting leaves contain a group of units with similar values of the outcome y. And cross-validation is used to construct a tree that maximizes predictive power without overfitting the data. Regularization penalty limits the depth of the tree. So the causal tree approach is going to extend decision trees to estimate causal effects. And so applying a potential outcome approach to decision trees requires altering the objective. So that is in a causal tree, we want the best prediction of not the outcome y, as in the regression tree, the standard regression tree algorithm, but the conditional average treatment effect. And so the causal tree algorithm is this adaptation of decision trees for causal inference that attempts to partition the data in a way that minimizes heterogeneity within leaf-specific estimated average treatment effects, rather than minimizing heterogeneity within leaf-specific outcomes. And so the difficulty in predicting the leaf-specific treatment effect is that we have no ground truth or no observed value of the true treatment effect, as we do when we're predicting the value of an observed outcome y. And this issue reflects the fundamental problem of causal inference. So we don't observe the causal effect for any unit. We always have that potential outcome, that unobserved counterfactual. And so to parallel the observed outcome approach, we're going to have to estimate a treatment effect for each observation. And so in addition to adapting the objective to maximizing this effect heterogeneity across leaves, we're going to draw on this honest estimation procedure, so that we're going to split the sample into training data for generating partitions and estimation data for estimating leaf specific effects. But we're going to need a modified expected mean squared error for the loss function that accounts for this honest estimation and the move to minimizing the mean squared error of treatment effects rather than outcomes. So the approach that Athey and Imbens developed allowed for standard asymptotic properties and in leaf specific treatment effects. So causal trees don't guarantee that confounding within leaves, the selection bias that we worry about in a study like the effects of college on wages, that it's addressed in these types of observational studies. So much of this work is applied to experimental data, but kind of expected to extend to observational data. Yet it kind of need to work out the particulars when using observational data. So here we're going to adjust for selection when we estimate leaf specific effects using nearest neighbor matching or weighting based on a linearized propensity score. And we also use a generalized random forest in the paper to show these leaf specific treatment effects. And then we want some kind of sensitivity analysis to try to understand how much unobserved confounding would influence the effect estimates for these different partitions. So to summarize, the causal tree algorithm proceeds as follows. We input data with the selected covariates with the full sample, and then we draw a random subsample for training, retain a holdout sample for estimation, grow a tree via this recursive partitioning and the training sample that maximizes heterogeneity across leaves and minimizes heterogeneity within leaves using cross-validation. This generates the structure of the tree, and then we feed the holdout sample into the holdout estimation sample into the tree, estimate these leaf specific treatment effects using matching or other adjustment strategies within the leaves. The result is this easily interpretable depiction of heterogeneity and treatment effects. So it allows us to identify subpopulations who may benefit most or least from a particular treatment, yet potentially, these particular subsets could have been unknown to researchers prior to analysis. One issue is that the decision tree may not be the one and only true tree. So an approach to avoid overfitting is to train multiple trees, an ensemble or random forest, and average their prediction. Stefan Fogger and Athey propose a causal forest, and also explore what we can do with the causal forest in the paper. And still we find in our application. So we wanted to get a sense of, if we do estimate this causal tree, how sensitive is it? How unstable is it to different splits? And so we find in our application that the tree we present here appears 95% of the time in a sample of 100 trees, and with a minor kind of modification for the final 5%. So it gives us at least some sense of, the stability of the tree. So back to our setup. Now we're going to again examine the distribution using, in this case, the recursive partitioning approach, where I'm still drawing on the same setup, the college completion by age 25, and now the ends outcome proportion of time and low wage work, age 25 to 50. And so the tree is color coded to align with the results based on that covariate and propensity partitioning, where bluer boxes here indicate stronger negative effects on, negative effects meaning that college reduces the proportion of time and low wage work. And so we focused on the way in which the tree and covers affect heterogeneity in particular branches with leaves that are blue versus yellow, and particularly blue leaves with large negative effects. So this primary partition is happening on mother's education, and this is now the full sample estimate. So our boxes indicate the treatment effect, the standard error, and then the percentage of the sample in that box. And then if we split, so now mother's education less than 12, these would be respondents whose mothers had less than a high school degree. We go to this side and we see this larger effect of college on reducing low wage work than among these mothers who had at least a high school degree. And which is even larger among those who come from larger families. So here, number of siblings are greater than or equal to 2. This is the yes versus the no. And we see this 32 percentage point lower level, which is even larger among those with lower social control. So this is a measure of psychosocial skills in the data. So those with low control above this threshold of about 10, and this is the yes. And in fact, this is the largest effect in the tree. So those whose mothers had less than a high school degree, grew up in larger families, and reported lower levels of control. And then we have a large effect among those who have go on this other side of having some higher social control, but who are men. And if we consider the other branch of those with mothers with at least a high school degree and lower measured ability have large effects as well. And we find the smallest effect for those with more educated mothers and higher ability. And here's actually 47% of the sample, and that less responsive leaf there. So the tree suggests that subpopulations with more disadvantaged, also those with a lower propensity of college, have larger negative effects on these outcomes, highlighting the other results. But while these are also kind of key theoretical axes, the groups identified don't fully overlap with those we explore with our theoretical priors. We have an R package that's complete, writing up a paper to go with it, with these kind of modifications to the causal tree package. So our R package is HTE tree with Xiaowei Xu and the statistics student at UCLA, Tanvi Shinkri, have worked on that a lot. And so we have these different kind of visualizations of the tree that I think are really nice. This being one of them, where this is a dynamic HTML version. It's interactive online here. This is just kind of a video representation of it. So that's included in the package. This produces the distribution of low wage work for the treated and control units, in this case, the college, non-college goers, and the estimated treatment effects, and kind of builds out the tree showing the categories that construct each leaf. This was actually designed by some researchers at Facebook and another corporation, Stitch, with that kind of put together what the visualization should look like. And then this is another tree visualization that Tanvi's been developing, which shows the density of the outcomes between treated and controls and the slope difference with both the raw and weighted estimates. I know this is a bit small to see here, but you can kind of focus in on some of these, some of those components. And then we can also focus in on these particular responsive leaves and evaluate how sensitive those effects are to unobserved confounding. So in this case, we subtract a bias factor from the point estimate and the confidence interval and the treatment effects obtained under unconfoundedness. So the bias factor is a product of gamma and delta, where gamma is the mean difference in the outcome associated with the unit change in some unobserved binary confounder, and delta would be the mean difference in the unobserved confounder between the college and non-college goers. And so suppose, for example, idleness unobserved in our data increases time in low wage work over the career and is lower among individuals who complete college than those who don't. And so we can have delta equal negative 10%. Then we'd assume the prevalence of so-called more idle individuals is 10% lower in the college educated than non-college educated groups, we let values of gamma range, in this case, from 10 to 40. And so we don't expect many unobserved factors to differ between college and non-college graduates by more than 10% for delta, given what we observe in our data among these really strong covariates that predict selection. And so things don't change much here is basically the story. So now we're focusing in on this part of the tree in the way this visualization that Tanvi created, and then just altering the values, these sensitivity parameters, and seeing how the slope shifts. And we could do that for various leaves within the trees, which we do it for I think all of them in the paper. Again, I said tree stability is a concern, so we made it get different trees if we generate different random splits of the training and test data. So we're including now a metric just to run, a certain number of trees and see how things look. And like I said, so 95% of the time we got this tree, and the other 5% it looked like this. We can also run the causal forest, and we do in the paper run 4,000 trees, and in this case you don't get a best tree. We've kind of had discussions with Stefan Fogger about this, whether we could kind of through the causal forest extract kind of best trees, which is a little more difficult, and then you have to decide what it means to be best. But the causal forest, it does, and the generalized random forest package that that they've put out allows you to rank the estimated treatment effects and then look at characteristics within these ranked treatment effects. So that's another approach. So what have we learned from the various partitioning strategies? So substantively, we find that more disadvantaged subpopulations have larger effects of college on reducing low-wage work. And we identify this with various strategies. Yet the groups identified by the causal tree are not necessarily those we might have focused in on. We don't want to go too far, though, in interpreting the specifics of the variables used for the splits. So instead, we want to kind of just think about those subpopulations identified by the splits. And so what we do in the paper is consider these descriptive statistics of the populations identified by the leaf specific splits. And so if we consider subgroups in leaves 3 and 9, what we're calling leaves 3 and 9, those ones with the largest treatment effects, we can kind of start summarizing other characteristics. So this is now the subgroup leaf 3. They had low parental income. They attended high schools that were more disadvantaged. I should have said low measured ability, low ASV, AB scores, low levels of parental education. Of course, the split was on mother's education, so we know that at least the mothers don't have more than a high school degree. Fathers had generally below average levels of education. The majority were Black or Hispanic. So even though we didn't see a split on race, this is an important factor that summarizes the subgroups here. The low social control, as you saw, and a low estimated propensity of college. And in leaf 9, we have kind of a different subset of responsive individuals where they have more average parental income, average school disadvantage, also share this low measured ability, more average parental education. The majority here were white and had also low social control and a low propensity of college. So we had these kind of somewhat two distinctive responsive subpopulations, those who are socioeconomically disadvantaged, majority Black and Hispanic, with individuals who have more average socioeconomic status, but still this lower below average measured ability. And about 95% had a low propensity for college in both of these leaves. And so that also summarized the patterns here. And then with leaf 7 and 10 were the least responsive subgroups here. I'm just focusing on leaf 10, who had high levels of parental income, low levels of school disadvantage, high levels of measured ability, and more educated parents. They have the highest levels of advantage and the highest propensity of college among these partitioned subgroups. So these were individuals who were most likely weren't at risk for working in low wage jobs, whether they completed college or not. They maybe could draw on their advantaged social backgrounds to avoid such employment. And again, these causal forests with 4,000 leaves, where we rank the estimated treatment effects, have these similar substantive groupings. And so finally, I just want to quickly go back to the question of interpreting heterogeneity in effects. So as I mentioned, by focus on heterogeneity, particularly by the propensity score or covariates that roughly indicate differential selection into college, we're led to ask to what degree we interpret the pattern in effects as representing difference in effects by observed versus unobserved selection. And we can run these sensitivity analyses, but we can also think about this theoretically, that some unobserved factors may reflect individual resistance to college. And so we could define the effect of college on wages to be a function of both this observed propensity for college and some unobserved resistance to college. And then in this figure, just the dark blue shaded regions indicate these larger treatment effect magnitudes. So the unconfoundedness assumption that we've invoked is the special case where the treatment effect varies by P, this propensity, but not by U, or we ignore U. But substantively, we take this lower resistance to indicate that individuals choose college because of anticipated high returns, and lower resistance gives rise to these large observed effects. So we note this correlation, potential correlation between P and U among college graduates. So low values of P, the estimated propensity, the estimated effect, though it includes proportionally more individuals have these low values of unobserved resistance. And at high values, we have of P, the estimated effect would include more heterogeneity with respect to the population in terms of this unobserved resistance. Like I said, most high propensity goers may just go because it's kind of the norm and expectation of their social background. So we're assuming unconfoundedness. They're informative in their own right. If it's true, we can interpret the effect pattern as a function of the likelihood of college. If it doesn't hold, we have these heterogeneous responses to latent dimensions of college, but still indicate variation in effects of college by this latent dimension of unobserved resistance. And importantly, if we focus on the diagonal, we find that among the students who are at the margin of indifference between college or not, those who appear less likely to attend college would benefit more from college. So this theory of positive selection is the very thing that causes the observed pattern of negative association between a propensity and the returns to college among students at the margin. So that has implications for public policy. If we focus on expanding college to those on the margin across the propensity of college, we have these larger expected gains. If we focus on those with a low propensity, or even those if we just expand to those with a low propensity, whereas if we expand mostly to those with a high propensity, we might have smaller expected gains. So just to wrap up here, heterogeneity in response to common treatment is quite common. It's unreasonable to think that people respond identically. In fact, homogeneity is a stronger assumption than allowing for heterogeneity. One longstanding approach is to determine subgroups of interest who we theorize should respond differently, and then test those possibilities. There's a lot of advantages to doing that, as we may have theoretical interest in whether black college graduates or white college graduates or men or women or those who grow up in disadvantaged versus advantaged are differently affected by particular circumstances, or our policies may target the recruitment of certain students and we want to know the expected gain. Or we want to know whether people with a low likelihood to complete college benefit more or less, because it gives us some knowledge of the stratification process and the consequences of unequal distribution of scarce resources. But those decisions are all made by researchers, and our data can tell us something that we hadn't thought of. So data-driven discoveries are common, yet the practices we often go about them can be problematic and not move us beyond our expectations and inherent biases to explore some other subgroups. So here we've adopted this machine learning approach to study causal effects that allows for uncovering important sources of heterogeneity. I think decision trees are an attractive tool for social science because they're not black box algorithm. The criteria are transparent. to the end user. Examining patterns of treatment effect heterogeneity over the life courses led to tending to outcomes that may be more relevant for more disadvantaged subgroups, like circumventing low wage work. And so we should focus more on these diverse outcomes as we consider returns for diverse students, and as we consider more treatment effect heterogeneity, sometimes it informs our the outcomes and what we should think about. I think the causal trees helped highlight particular subpopulations of interest, as well as validating some of the characteristics that we've previously considered. And I will stop there. Thank you.
Thank you very much. We can now open the floor for questions. So if you have one, just